Hello everyone. Today we will be doing Reimer Tiemann reaction. This reaction is very important, especially for the students of class 12. This reaction is important for boards as well as competition. Now in this video we will be doing the reaction as well as the mechanism of Reimer Tiemann reaction. Before beginning, we must know the starting and the end product of this reaction. The reactant of this reaction is phenol. We'll start from phenol and we'll end up with salicylaldehyde or salicylic acid depending upon the reactants or the intermediates we are taking. Let's start with the reaction. Here we have phenol. We'll add NaOH, that is sodium hydroxide, which should be aqueous in phenol, and the reaction proceeds as this. We get sodium phenoxide, that is ONA on the benzene ring. This is called sodium phenoxide. Let's see how we got sodium phenoxide from phenol. From here H and from here OH, that is water is removed and this sodium attaches to this oxygen and we get sodium phenoxide. Now this sodium phenoxide will be used for further reaction. Now we take sodium phenoxide and we add chloroform to it, that is CHCl3. We write it in this way. This is chloroform. Now from this chloroform and this sodium phenoxide, at the ortho position we have hydrogen on the benzene ring, that we know. Now from here we remove this hydrogen and from here we remove this chlorine, and we have to put some conditions like temperature 340 to 343 Kelvin, and we have to put sodium hydroxide. Now from these two molecules we can remove HCl and the product will be this. Here the remaining part of chloroform, that is CHCl2, attaches on this position of sodium phenoxide. Here we get CHCl2 and the ONA part of sodium phenoxide remains same. Now in this product we will put NaOH at 340 Kelvin. What happens? The ONA part remains same and the CHCl2 part, in this part both the chlorine atoms converts into hydroxyl groups. That means we can write it as CH, same, and the chlorines can be written like this. They are converted to hydroxyl groups. And this is an intermediate. Also, we have hydrogen here and we have sodium and here chlorine. So, sodium chloride will be removed. That is, 2 molecules of sodium chloride has been removed. Now in this step, it is clear that from 2 hydroxyl groups we can remove 1 molecule of water. Like this. So we get the rest part of the molecule remains the same, that is ONA remains same on its position, CH remains same. Now from here 1 water molecule is being removed, so we will write minus water, and here 1 bond with oxygen is left, so it will become double bond O, right? You may see that this molecule is similar to salicylaldehyde. The only difference is we have Na here in place of hydrogen. If here would be OH, then it would be salicylaldehyde. To convert it into salicylaldehyde, we will put dilute HCl to it, right? When we add HCl, sodium chloride is removed from here. Chloride and sodium ions both combine to form NaCl, and this hydrogen attaches to this oxygen and we get salicylaldehyde. This is OH and CH double bond O plus what we got here, NaCl. This is the main product of this reaction, which is salicylaldehyde. As I told you earlier, that in this reaction we can get two products depending upon the intermediate or the reactant we used. So, if in the place of chloroform we use carbon tetrachloride, then in the place of salicylaldehyde we will get salicylic acid. Let's have a look. Now, to make chloroform, to make carbon tetrachloride from chloroform, just remove this hydrogen and put one chlorine here. So this becomes carbon tetrachloride here. Right? So this is carbon tetrachloride. Now here we have 4 chlorines. We have removed one chlorine from here, as we have done in the first reaction. The procedure of the whole reaction for salicylic acid is same as that of salicylaldehyde, right? The only difference is of carbon tetrachloride. So here we have added one chlorine, so it will become CCl3. We have removed one hydrogen also, so it will become CCl3 in place of CHCl2, right? The reaction is same here also, but now we are adding NaOH. So these 3 chlorine atoms will convert into 3 hydroxyl groups. 1, 2 and the third one is the hydrogen. This will also convert into hydroxyl group OH. Right? Now from here water is removed and we get C double bond O and OH will remain same here. OH. Right? The reaction is going on the same way as that it was in salicylaldehyde. Again, NaCl will be removed and OH again here, OH. And we get salicylic acid. Now let us look at the mechanism of this reaction. In this video, I'll be showing the mechanism of salicylaldehyde. The mechanism of salicylic acid will be same of that. Just the difference will be of carbon tetrachloride in place of chloroform. Okay, let's draw a molecule of chloroform. That is CHCl3. This is chloroform CHCl3. As we know, chlorine is electron withdrawing group by inductive effect. So it will withdraw electrons from carbon and hence carbon will withdraw electrons from hydrogen. This is called minus I effect, that is minus negative inductive effect, right? So due to this electron transfer, what will happen? Hydrogen will attain a partial positive charge and all the chlorine atoms, the carbon atom will attain a negative charge, right? So this is because of minus I effect. Due to this minus I effect, hydrogen of the chloroform will become acidic. So we can say that chloroform has an acidic hydrogen. This will be used in the reaction. Okay, the first step of the mechanism is we will take NaOH and it will be converted into ions. It will give Na positive and OH negative ions. This step is a fast step. The second step will be CHCl3, that is chloroform, and we know it is partial positive and it is partial negative. We take chloroform and to this chloroform we add this OH negative ion, right? OH negative. Now these are the electrons of this chloroform, CH bond. Now what will happen? This H plus will be transferred to OH negative. That means water is formed combining H plus and OH negative, and the remaining part, that is Cl3C negative, will remain, right? And here these two electrons, one was of hydrogen and one is of carbon, these two electrons will remain with the carbon atom because we have taken out H plus from this chloroform. H plus means it doesn't have any electron. So both the electrons will be with carbon atom. Now the third step of the mechanism is we will write down this chloroform in this way. Negative. I have just written the chloroform by spreading the chlorine atoms on the carbon, just showing the bonds, right? Now we said that these two atoms are with carbon. Let's show it here. These two electrons are of carbon and chlorine. This chlorine and this carbon, these two electrons are of these two atoms. Now from here, these two electrons and this chlorine atom are being removed, including this negative charge from here, and this is also a fast step. The second step was also a fast step. From here Cl negative is being removed. Whenever we put negative, that means it contains both the electrons, and whenever we put positive, that means it doesn't have any electron, the shared electrons, right? So Cl negative, because the chlorine atom is taking both the electrons, so we will write it as Cl negative. The remaining part will be CCl2, right? And we will write this 2 electrons with carbon. Now you'll be thinking that we have given both the electrons to chlorine, then why are we writing these 2 electrons with carbon? So you must remember that these 2 electrons of this carbon, we have not drawn these 2 electrons here. These electrons were only of chlorine and this carbon. These electrons were not drawn here, right? So now I draw these 2 electrons here. Don't confuse these 2 electrons with the electrons of carbon and chlorine. I've just not drawn it here so that it might not confuse you with the chlorine electrons. This is called dichlorocarbene, and this is an electrophile, right? Dichlorocarbene because it has 2 chlorine atoms. Now look at the fourth step of the mechanism, and this is the main step of this mechanism. We'll take phenoxide ion. What is a phenoxide ion? It is when H plus is removed from, this is phenol, we just remove H plus and the remaining part, this is called phenoxide ion. That means O negative. Because we have removed H plus, that means both the electrons are with oxygen. That means oxygen will contain the negative charge, right? To this, okay, let me show the lone pair also. 1, 2, 3, 4 and 5, 6, right? And as per the reaction, we will show hydrogen here also, as we have shown in the reaction. Okay, let us draw the ring in this way so that we can show the shifting of the bond. Now to this we will add this dichlorocarbene. Alright, this lone pair will attack here. Just remember the position. This is the point where hydrogen and all these bonds are meeting. At this junction, this bond will shift here. Now, this bond, the bond between the carbon attached to oxygen and the carbon attached to hydrogen, this bond, this pi bond, will shift to this point. Right? Both the bonds are shifting here. What will happen? Firstly, this lone pair will be shifted to this bond, and this bond will further shift to this junction. Right? This will be a slow step. That means it is the rate determining step. That's why it is the most important step of this reaction. Now what happens? As we have shifted this lone pair to this bond of oxygen and carbon, hence a double bond is obtained by carbon and oxygen. Right? Now we have donated the lone pair of the carbon to this carbon. So this carbon, that means the carbon of carbene, will also make a bond with the carbon of benzene. That means here we get CCl2. And the hydrogen will remain same because it is not performing any action here. And the other two bonds also remain same. These two bonds. Right? Also, carbene will get a negative charge here. This carbene will get a negative charge because we are also shifting this bond here. That means this we are donating these two electrons to this carbon, and this carbon will give these electrons to the carbene. That means carbene will get a negative charge. Now from here, this hydrogen will attach to the carbon, this carbon, and this bond will be shifted here. Just look at this step very carefully. Hydrogen is shifting to carbon of carbene with negative charge, and this bond of hydrogen is shifting to the carbon-carbon bond of the benzene ring. Right? So what happens? The ring as it is. Here we get C, that is carbon of carbene, and two chlorines, 1 and 2, and one hydrogen that now attached to the carbon, and the rest part remains the same. Now this bond also shifted to this bond, so one double bond here also. Right? Now the last step is the fifth step. Here, this part, I am showing this again here. Okay, one more thing we have to do in this step. We will shift this bond to oxygen again, and this will become a single bond with oxygen, and oxygen will attain a negative charge. Right? Let's draw the structure again. Oxygen with negative charge, carbon with 2 chlorine atoms and 1 hydrogen. Right? Now we will add 2 NaOH molecules as we have added in the last step of the reaction also. So here sodium chloride will be removed, 2 molecules, and we get this ring. I can show it with a circle, O negative as it is, and here what we get, OH and OH in place of chlorines. Now can I show this OH bond like this? Right? Now both the electrons of oxygen and hydrogen shown in the center, and the electrons of carbon and oxygen shown in the center. Now what I will do is remove this OH and this H from here. That is, I'm removing one molecule of water from this, right? And these two electrons will be shifted to oxygen because nobody is taking, so oxygen will take it, right? So the end product will be, let me draw it here, it will be salicylaldehyde. O negative as it is. This will be carbon. This carbon here, this oxygen getting the lone pair, so it will make a double bond with carbon, and this hydrogen plus water which we have removed from here. Now the sodium in the first step will get attached to the O negative ion here. Na positive will attach here. We get ONA. Now on adding dilute HCl here, we get salicylaldehyde. I can draw the structure also. This is OH, that means ONA changes to OH, and CHO, the aldehyde group, salicylaldehyde, right? So this is the mechanism of Reimer Tiemann reaction. Thank you.